Good afternoon and welcome to this Chemistry World webinar. I'm Ben Valsler, Chemistry World's digital editor. Now, as you can see on screen today, we're going to discover the possibilities with the new multi-sample Discovery X3 differential scanning calorimeter. I will tell you a little bit more about what's coming up and introduce our guest in just a sec. But first of all, let's just go through some basic housekeeping for GoToWebinar events. You may or may not have used GoToWebinar before, but for most people, it will appear as a panel on one side of the screen. In that panel, you'll have the ability to control what you're hearing, move some things around, and importantly, to ask questions. So there is a box at the bottom of that will allow you to ask questions to our speaker. Now, you can ask questions at any point throughout the webinar itself, so don't feel that you need to wait until the end. As soon as something occurs to you, just get your question in there. We'll be putting them to our speaker at the end of his presentation. Now, other key things to note, there will be a presentation today, but we won't be sharing the slides from this. We think it's important that you get the slides in the context of what's being said. And so rather than sharing the slides, we'll send you a link to the recording of the webinar. Now, that means you can come back whenever you want to, watch it again, pick up on anything that you missed, just clarify those points that you didn't quite catch first time. And all of that will be available to you in an email that we'll send out in a couple of days' time. And for those of you who attend live, welcome, thank you for joining us. In the same email, we'll include a link to a certificate, which is just our way of saying thanks for attending the webinar live. And really is how these webinars work best, when you can actually attend live and engage with our guest. Now, today's topic, we'll be looking at the X3 DSC. We'll be seeing how it can improve sample throughput and provide greater confidence in your analysis. We're joined in particular by Jason Saienga. As you can see a picture of him on screen. He's going to pop his webcam up in a bit as well. He's from TA Instruments, and he's been there since 2006 after doing a doctorate in material science and engineering at Iowa State University. So he can walk the talk as well as talk the walk. And he's a product manager for TA, and his team work to define and coordinate all of the future thermal analysis and thermal conductivity product lines at TA. Over the course of the next hour, he's going to help you to understand how the X3 DSC can provide critical information about a material faster and with an increased level of confirmation. We will see how the X3 DSC can help to streamline testing needs in a QA and QC environment, and we will visualize the ease of gaining statistically relevant data in a single test using the multi-sample X3 DSC. So the next person you should see should be Jason. We'll hand over now. Keep those questions coming in. Thank you to everybody who has joined us live. I'm sure you will enjoy Jason's presentation. Jason, let's just see if we can see you and hear you. We can see you, that's a good start. And I think we can hear you as well. Thank you for joining us.
Thank you, Ben. Appreciate the introduction. Welcome to everyone. My name is Jason Saienga, as the introduction said. I am the product manager for TA Instruments, and today we are going to be talking our way through the X3 DSC. A little added bonus, we're going to talk a little bit about some both hardware and software features that that we have that are relatively new that will hopefully really help you advance your testing capabilities and your testing needs in your labs. I'm going to save some bandwidth here and turn my camera off, we will walk through this journey here. So as many of you out there may have in your labs, you may have a DSC. You may be familiar with DSC and what it can do for you. The Discovery X3 DSC is a multi-sample variation of that DSC, and so the X3 DSC is going to be able to provide high-level heat flow data with up to 3 samples simultaneously. So you can see here, picture up here in the upper right-hand corner. Clearly the advantages, some of the obvious advantages obviously are higher throughput. You're running potentially 3 samples at once. You're combining the efforts of 3 instruments into 1 instrument, so you're saving bench space. And potentially, if you're working with liquid nitrogen coolers, or you're working with, you have gas bottles that are supplying your purge gas, you might have lower consumable costs with a single system like this. But as we're going to talk about today, and I'm going to present to you today, there's going to be some other advantages that you're going to see with the opportunity to run 3 samples at once. And so we have the ability to increase the confidence in interpretation. Generating 3 sets of data gives you statistically relevant information in a single test. You have opportunities to look at your data in real time and get, if all you're trying to gather is some qualitative validation, you're going to see that real time, as well as testing along with standards and controls, and ultimately condensing 3 tests or 3 samples measurements into 1 experiment gives you much more time for research, gives you opportunities to dig in and dive into the material a little bit deeper than maybe you had were willing to do with a single system where you're running everything 1 sample after another. So we're going to walk our way through some examples of this. So the X3 DSC is it is somewhat of an adaptation to our standard single sample systems. Uses an enhanced Tzero heat flow signal. That Tzero technology and the 4-term heat flow equation that we utilize as part of our Discovery DSC series, really does provide sensitivity and reproducibility that just on its foundation gives you the confidence that the results that you see are accurate. That we have very good baselines, very sensitive systems. So we know that there isn't going to be a need to do any kind of pre or post test manipulation to get the data to look better. It's going to look better, and it's going to give you just a level of confidence right from the get-go that your results are indeed accurate. So, a single test can provide numerous benefits. Obviously, as I mentioned already, 3 complete data sets in a single run, real time, easy to see comparisons, simple identification of variations in your materials, or even a validation with a control or a standard. And so you can see in this particular example, what would have taken us either 3 instruments to accomplish or 3 tests run in series, you can see that we have made 1 measurement and we have 3 samples of varying levels of impurity. So, regardless of what our numerical or quantitative results show to us, here you can see that it's very easy to detect a variation in these from the pure to the slightly impure 0.7% to the 2% impurity samples. So obviously, once we quantify that, it's much easier to see. But without you've made 1 single test and you've been able to get at least a qualitative evaluation that there is some significant difference between these 3 samples here. So if we look at just some, I'll say some basic, polymeric type materials, we'll present, thermosets. Thermoset is a cross-linking material. Most of us might be familiar with it, in our 2-part epoxies, 5-minute, 1-minute, 10-minute epoxies that we work with. But thermosets are commonly found as adhesives. They're sometimes used in high-performance composite. They're materials in electronic PCBs, construction materials, and so forth. DSC is used to measure the curing exotherm, so the amount of heat that's generated during this reaction as we're going from our 2 parts to our single, like intertwined, chained structure. And so we can see both the exothermic cure from that reaction as well as the glass transition associated with that structure, or even the glass transition as it moves through the various cure states. And thermoset failure is commonly associated with a non-uniform cure. So if for whatever reason, our part A and part B don't get full mixing, or there's pockets of concentration of A and B, you might see that there's some sort of a lack of chemical reaction. So you might see a reduction in the exotherm, or you might see a variation in the glass transition. But as we know, with as we are maybe commonly aware that with epoxies, once you put part A and part B together, there's a very good chance that given enough time that that's going to cure, whether it's a 1-minute epoxy or a 5-minute epoxy. There's some amount of time that reaction is taking place. Regardless of how well it's mixed, you're going to have some reaction. And so, certainly in an instance where a material might have some sort of time sensitivity to it, or maybe there's an environmental sensitivity to that material, being able to take 3 samples all at one particular time, prepare them at the same time, and put them into a DSC at the same time gives you a lot of confidence that I know any variation I see in that material is then directly associated with a change in composition or a mismatch in the cure schedule. And so, here in this particular example, we've taken 3 different epoxies, or the same epoxy that has been cured at various times. And so we have an uncured epoxy in the red. 15 minutes later, a 15-minute allow that material to wait 15 minutes, and then allow another material to wait for 60 minutes. Place them all into the DSC at the same time and make this measurement. And you can see in this particular instance, we have the epoxy that was cured for 60 minutes has a much smaller exotherm, because most of it has already cured as it's been sitting there, versus the 15-minute epoxy and the uncured, which is a material that was mixed up just before it was placed onto the DSC. So the amount of exothermic reaction that we see there is associated with, we'll say, the total cure of that material. The other 2 are fractions of that. But you can see, if an epoxy was, let's reverse this a little bit, and you can say, well, I have an epoxy. I want to know, different formulations. Maybe I want to know, how each of these are going to react under different conditions. If I wait for some amount of time between sample 1, 2, and 3, there's a potential that you're going to get some variation in these exotherms, and then it may not be able to tell you that really the information that you're hoping to capture in the DSC. And so having an established time zero certainly provides a good good level of confidence, good starting point, and the results that you then see have a lot more weight to them, because you know that you've made the measurement at the same time. Now, if we take that same sample, cool it back down, and reheat it, you can see that the glass transitions in this case are all about at the same temperature. You can see that we no longer have any exothermic activity. So, heating them up to the initial temperature and cycling them through gives us an indication that we've gone through the full cure. Going back through this this heating cycle, you can see that the composition in these cases must be about the same. So maybe we could make the conclusion that the samples had gone through different curing schedules or different processing. But in each case, we've made, let's say, 1 test, made up 3 samples, made 1 test, ran through a heat-cool heat experiment, and we have 3 data sets that we can then either formulate some sort of conclusions and comparisons, or be able to take that data and look at a statistical relevancy. If we move into sort of the other areas of polymers, we look at some semi-crystalline thermoplastics. These are going to be your plastic bottles, plastic containers. Many of these are semi-crystalline, so they're going to have some crystalline phases, potentially some amorphous phases. There's going to be various concentrations of each. Obviously, formulating a polymer, formulating a thermoplastic with different additives, or processing it in some way, is really in an effort to either modify the concentration of a crystalline phase versus an amorphous phase. And in those cases, you're going to associate those phases with a performance metric, some end use case where it has to be flexible at room temperature, or it has to be able to withstand some impact and those sorts of things. So you're going to try to formulate a material so that it has the right properties. And so it might be that you're taking in raw material and you want to know whether the raw material is what you expect it to be. It could be that you have 3 different production lines. Maybe it's 3 different extruders, or however the material might be processed, and you want to know, maybe it's a QA kind of environment where you want to know that the materials that you're producing are good, through that production process. So in this particular case, we can see that we have 3 different 3 PET materials, various there are various states of quench. So PET is as received in the red, cooled at 20 degrees C per minute, so given some level of thermal history, and then the PET in blue is a quench cooled version. So you can see all 3 of these have some varying states of crystalline melting, cold crystallization here around 150 degrees, the blue curve having the most cold crystallization, the red curve showing no signs of crystallization, and then a melt peak here out closer to 225, 250 degrees. And obviously, with a material that goes through cold crystallization, we know that as we received it, it was highly amorphous. The red curve here, we see a very small glass transition, so probably highly crystalline with some amount of amorphous material. And so this, like I said, this could be 3 samples from different incoming barrels of material or lots of material. It could be that this is your sample that you've taken off of 3 different production lines, but you've been able to establish a time 0. You've been able to establish that it make one measurement and get 3 data sets. Pardon me. If we take those same materials, cool them back down at a controlled rate of 10 degrees C per minute, giving them all the same thermal histories, you can see that each of these cases, the glass transition is about equivalent with one another, and the enthalpy is right around 30 joules per gram in each of these cases. So, regardless of how the material looked in its first scan, again, we've made one test, been able to run through a cool heat experiment, collected 3 data sets, and in this case, we could draw the conclusion that the composition seems to be about the same, because, or we assume that it is the same in this case. We've controlled the cooling, controlled those rates, and we've been able to see the similarities between the materials rather than in the first case where we might be seeing differences. So, maybe it's a material that it comes off the line, and you're taking a sample at the top, the bottom, and the middle, the front, the beginning, the middle, the end, side to side. Maybe that shows you variations, but obviously the concentration or the composition of these materials is the same. But we could also look at it, on a sort of a different lens and look at it on the cooling curve and say, well, maybe we're adding in materials that are nucleating agents, or we're adding materials that we think might be impacting the ability to process this material. And so here in this case, we look at 3 different materials, 3 different PETs, samples on cooling, and you can see there's a lot of similarities between the blue and the green curve. The onset of crystallization on cooling is about the same, slight variations, but you can see that there is a significant difference in the onset of crystallization in the red curve. And so again, if you're concerned about the way that a material is being processed, or you want to try to improve the nucleation or the crystallization by adding nucleating agents, you might be able to look at 3 different materials here in this case and get an idea, very clear picture that that whatever additives you've placed into the material, however it's being processed, or are potentially going to impact the end result of this material. Now we can take it a step further, I guess, and look at the heat capacity. And so heat capacity in most cases, will run with run under modulated conditions. Heat capacity can be a value that you collect that is that is used in determining the amount of energy that's required to put into a system. You might be looking at heat capacity just in terms of molecular mobility. A low heat capacity is low mobility, high heat capacity is higher molecular mobility. And so in this case, we're running a modulated experiment. And for those of you that are familiar with modulated DSC, they're commonly run at 2 or 3 degrees C per minute. So they're relatively slow experiments compared to the 10 or 20 degrees per minute rate that you would commonly run standard DSC experiments. So, one may say, well, I have a very busy schedule. I have so many samples, such a backlog. I just can't spend the time to run modulated to get accurate heat capacity. But in this particular case, you can now make 3 measurements at once. And so these materials have similar temperature ranges for the experiment. We can throw a Sapphire standard in to one of our 3 positions to verify that the heat capacity that we generate is indeed accurate. But you can see very clear glass transitions for PET, clear glass transition temperature for polystyrene. So in each of these cases, we get an accurate measure of TG plus a quantitative value of heat capacity for each of these 2 materials. And we have essentially saved some time and allowed ourselves the opportunity to dig in a little bit deeper and investigate these materials in a little bit more detail. So that kind of moves me to another type of materials that we would commonly test, and this is more suited for the pharmaceutical type materials. But looking at material compatibility using the DSC, it is certainly a tool that can be used. In many cases, especially in pharmaceutical materials, active ingredients and excipients, have to be compatible with one another in order for them to have some level of shelf life. If these components that are in an aspirin tablet or a Tylenol tablet or some other medication, if they're not compatible with one another, as they sit in your shelf at home, your cabinet at home, there's a potential that they're going to lose the efficacy. It's potential that they're going to become toxic. And so understanding whether these interact at under normal conditions is certainly a critical analysis. And in some cases, you can use instruments such as HPLCs to determine whether there's a chemical change that's taking place. But certainly DSC, modulated DSC, and TGA can give you some indication as well. And it's in many ways, it could be a very simple test. And I'll show you how we can run those tests here in a second, and how the X3 provides some benefits there. So, if we were simply just looking at incompatibility between 2 materials, we could take the examples here of aspirin, magnesium stearate. We want to understand whether these 2 materials are stable with one another or compatible with one another. You can certainly run a 50-50 mixture in a standard DSC, and you'll see the result here in the green curve where we have 2 peaks. But you might without running your standard materials or your mixed materials in their pure state, you're not going to necessarily know whether those 2 peaks represent aspirin and mag stearate. And so you can, with the X3, obviously you can run your 2 pure materials alone, as well as your 50-50 mixture. And if these 2 materials were truly compatible with one another, they would simply show the peaks that represent each other in that green curve. And here you can see, as we ramp through temperature, you can see that we see 2 peaks that are not at the same temperature of our pure aspirin and pure mag stearate, which gives us some indication that there is some incompatibility. Now, in this particular example, we're ramping it to higher temperatures. So that's certainly a method to look at compatibility. But obviously, as we increase temperature, the reactivity might change, and we're not going to we're not going to have, our bathrooms or our homes or the place, even a a shipping truck or a delivery truck out in the hottest places, in, let's say, Death Valley here in the U.S., they're not going to see 100 degrees C. They might not even see 80 degrees C. So, that's where we can take it a step further and say, well, I want to know what the compatibility of these two materials might be at a more, a more reasonable temperature. And so here we can make a measurement at isothermally at 50 degrees. Now, this requires the benefits of modulated DSC, where we can hold isothermally at 50 degrees and modulate the temperature, in this case, 2 degrees, plus or minus 2 degrees every 200 seconds. We held this experiment for 24 hours. Now, in this particular case, where we're looking at heat flow versus time, you can see that the aspirin alone, mag stearate alone, the 50-50 mixture don't really show us anything. And that, that's fairly common. If the reaction, the energy was relatively small, you may not see something in the heat flow, since there's rate dependence with a heat flow data set. And these experiments could be tested on a TAM, something that looks at much smaller energies, nanowatts of energy over long periods of time. But like I said, there are some tools here that can help you. And so if we take this modulated data, and instead of looking at heat flow, we instead look at the value of heat capacity, which is an absolute value and does not have any rate dependence. You can see here, over this same 24-hour period, there is the aspirin and the mag stearate in the blue and the green curves are relatively stable throughout that entire experiment. But you can see that the red curve, which is the 50-50 mixture, there's a constant rise in that heat capacity. And changes in heat capacity, as I mentioned before, are changes in structure, changes in mobility. And so the only conclusion that can be drawn here is that the 50-50 mixture, even held at 50 degrees, is not stable with one another. So, this experiment lasted 24 hours. And, obviously we can see that there's, pretty clear indication in, a fraction of that time that these two materials are not compatible with one another, especially in relation to the pure mixtures. But it's a relatively easy, simple test to put some powders into some pans and make a single test to get, 3 pieces of information. Now, in this case, we're looking at 2 pure materials and the mixture of those 2 materials. But if you've already run through the pure variations of those materials and understood that they have a level of stability all on their own, you could now start to work with different formulations. You could look at different concentrations. You could look at just totally different formulated materials and look at compatibility and using the same lens. So sometimes the test won't last 24. Sometimes it'll be 5, 10, 20. But this is in a traditional single sample system, you're going to end up tying up an instrument for very long periods of time. And this is, if we were to run these 3 experiments in some sort of serial fashion, that's 3 days of testing. And so that's probably where that's going to hurt your productivity. Most of us maybe don't have that kind of time. So that's where the X3 certainly provides added level of productivity of benefit. And so productivity isn't necessarily always defined as cranking through samples faster. Productivity could be getting answers faster or getting a clearer picture faster. And so in this case, we're digging in a little bit deeper, investigating a little bit further, getting a much clearer indication as to what's going on without tying up 3 separate instruments. So there is more time for research. There's more time to gather the information that is critical for us to move to the next step. And just like many of our other Discovery DSCs, there's still the 54 position auto sampler, so it's going to provide you a level of 24/7 operation, maximizing the throughput, whether it's running through lots of samples every day, or running through critical samples when it's necessary. We may not always have 100 samples to run every day, but there may be, a week where we get 50 samples that we have to test, in very short order. So, the X3 DSC certainly provides the opportunity to be able to get through that data much faster, so that we don't have to come in on the evenings and come in on the weekends to set up experiments and get the answers that we're looking for. There's also, flexible, there's automated calibrations and verifications, so we can, keep our instrument maintained. And then there's an automated position or a semi-automated position calibration for the sensor. So, for sensors, is placement of the pans on those sensors is critical for, the maintaining high quality data. Positioning the autosampler so that, or calibrating the autosampler position so that it maintains, accurate placement of those pans is critical. And so we've developed some routines to be able to do some of those things automated. So you have more time away from the instrument than you have to burden yourself with standing in front of it. Now there's also some other tools here. Obviously, as I talked about, connection between the sample, pan, and sensor is critical. Placement of the pan is critical. Preparing samples appropriately is critical. And if we're going to run 3 samples in the same time that it takes us to make 1 sample, having the tools that help us, get through that process a little bit faster are also going to be critical. Having 3 data sets or collecting data 3 times faster is only as good as the speed at which you can prepare samples and the speed at which you can analyze the data or generate results. And so obviously the powder loading tool here and the sample cutting kit are tools that we have available to give you a little bit more freedom to, or maybe a more streamlined approach to preparing samples, maybe less headaches regarding powder loading into a pan. So, there are tools there that are helping you speed up the sample production process, and then the pans and the press are designed to make it easy to load and seal those pans and get ready to make your measurements. Now, as I just mentioned, there's also the data handling and the analysis side of things, and so there are some productivity tools already developed for Trios, for every version of Trios, which is the software platform for control and analysis. There's a batch processing feature that allows you to actually establish an analysis template to your data. So if you're working through the same types of materials and you want to apply the same kind of analysis, you can associate that analysis with every run that you make. So all you have to do is weigh out your sample, place it in the tray. It's going to go through the run, and it's going to do the same analysis on every single sample that you are preparing. And so there's some consistency in the analysis, but it's giving you results that much faster. If there's a requirement to present these results or the data in reports, there are some report templates that you can have automatically generated, as well as control charting. So if you're trying to track, easily track, a particular material as a function of time, over the course of a week or a month or a year, you have the ability to send results over to a control chart and store those results and be able to work with those and see how data is trending. Are glass transitions moving as a function of time? Is our enthalpy, is the melting enthalpy changing? Is the crystallization behavior changing? And so you have a very good, clean way to do that. And this provides, the batch processing component, at least this side of it, allows you to automate that process. But there's also, times where, maybe we didn't know how to analyze the data when we first collected it. And so we just have a whole collection of data files that we need to work through. Again, could be very time consuming, but we also have the batch process associated with a stored collection of files. So if we have historically collected a number of data sets and we want to now start to do some control charting, we can select a group of data files and apply the same analysis to those data files, as well as create reports and send results to control charts, all in is sort of a single action item here that again helps ease the burden a little bit on the fact that you are now collecting data faster. Because just because the instrument can do it doesn't mean that our job is done. There's sample prep, there's instrument time, and then there is analysis and reporting, which is equally as critical as the performance and capabilities of the instrument. If we're trying to find answers and we're trying to advance our research and we're trying to be able to provide, that critical information sooner, all of these pieces, ultimately need to work together in order to give us that streamlined approach. But I'd also like to, introduce you guys to another feature that we have brought onto the thermal product line. It's been available for rheology for some time now, but it's Trios Autopilot, which it's a premium Trios feature, and I'll walk you through it here in a little bit. But ultimately, you have the opportunity to design and develop sort of streamlined interfaces, provide guided operation for whatever your standard operating procedure is, for your methods, for your procedures, for sample prep. There's a number of different benefits that allow you to easily create automated routines and get repetitive operations faster. Okay, so ultimately, Autopilot is, it's a routine development window. So you can see here just an example, quick example, where you're using blocks of I'll say simple programming, a simple programming language that gives you ultimate control of both instrumentation, instrument control within Trios, as well as data analysis, reporting. You can use variables, equations to set up criteria. But it's a relatively simple and straightforward method to create what we call a script. And so you can run through a script. Essentially, it's running through a program where you can ask Trios to do many different things. You can ask the DSC or the TGA to do a number of things. But the opportunities that you have here is to be able to simplify the interface. If you're running the same or similar experiments, or you have a specific experiment tied to a particular operating procedure or a particular method or a specific production line, you can simplify the interface so that you're always going to the same place, running the same test, and running the same type of analysis. And so that really allows you to capture results and capture information a lot faster. There's a reduction or a reduction of the burden for training if you can develop guided test setups. So if there's only specific information that a particular user needs to enter in, you're guiding them to that specific piece of information. Here I have an example of there's a video here of loading on a rheometer. Obviously loading on a rheometer there's a little bit more finesse to it, but certainly working through videos for sample pan preparation and so forth, all of those sorts of things can be incorporated using Autopilot. And you can program it to give you very easy pass-fail criteria. You can tell it show me a green light or a blue light or a red light rather a red text or green text if the sample is good or bad. And so there's certainly a lot of flexibility in regards to Autopilot. So if you look at just the common challenges within analytical labs, maintaining operating procedure compliance, making sure that we're going through the same steps between operators, between days, between various instances, making sure that all of that sort of stuff is compliant is critical. Operator training, as new people come on board, as more people come on board, as your production increases, as the needs increase, being able to reduce the amount of time it takes to teach and train operators on every little instance of a sample prep, method development, analysis, and reporting. Those things are, reducing the burden there is certainly helpful in productivity. And again, advanced calculations, whether we're just doing pass-fail conditions or whether we need to do some more advanced analysis or computational analysis on the data. Again, each lab is going to be different, and so maybe some or all of these are pertinent to you. But the Discovery X3 DSC provides that increase in sample throughput, maximizes lab space by reducing bench usage, reducing consumable costs from purge gases, liquid nitrogen, and so forth. But ultimately giving you, just in the instrument alone, more confidence in the results, more confidence in the interpretation that you might see. Having 3 samples tested at once eliminates the variability that, oh, well, I ran this one day and then I came in the next day and the results were different. Is it because the day was different, or the user was different, or the technician was different? Having those 3 samples run at the same time certainly provides an increased level of confidence in your interpretation and your evaluation. But then, Trios Autopilot, creating a simplified interface with guided operations, is improving data precision and potentially increasing productivity and reducing training time. So the combination of these two things here become extremely powerful in terms of furthering your research and development, maintaining high quality of incoming supply, or the high quality of outgoing material that you're trying to produce. And so again, getting those answers, that critical information sooner, faster, and easier is all ultimately going to make our jobs a lot easier in terms of research and development, material characterization. So with that, I appreciate the time you spent, and I believe that we have a fair amount of time for some questions. So
we do indeed. Thank you so much, Jason. That was a very in-depth presentation. We've only had about 40 minutes with you, but we've covered a lot of ground there. Hopefully that will have been a really good overview to all of our audience. We've had a few good questions in, but that doesn't mean that you have run out of time to ask questions. Please do keep them coming in. Little reminder for those of you who missed the very beginning of this presentation, we don't share the slides from this. What we will do instead is send you a link to the recorded version. So if there was anything that you missed at the start, you'll be able to catch up on that in your own time. We'll also send everybody who attended the live broadcast a certificate to say thank you for joining us. But yeah, do keep your questions coming in. I'm making about 17 minutes, so we should be able to squeeze some good questions in. There is one that occurred to me, Jason. Jason, would you mind putting your camera back on now that we're not seeing the presentation? It'd be lovely to see your face. Thank you. One thing that occurred to me, if people are used to an older generation of DSC, clearly there are some novel features here, all of those things that save time. What's the learning curve like for somebody to go from an older model onto something like the X3?
Yeah, certainly, there is no learning curve. If you have used a standard DSC, if you've used one of our Discovery DSCs, and I'll say even maybe the generation before that, there's little to no learning curve. A few more boxes to enter information, but the box in terms of sample names and pan masses and sample masses, really don't change. And the fact that you're only setting up one experiment, obviously the 3 samples are being tested at the same time. They're going to go through the same test method. But it's one method that you're pretty accustomed to setting up, and the rest of the information is the same as you would normally work with under standard conditions. So the learning curve is, if there is a curve, it would be very small. It would be it's just walking up the beach from the ocean, really.
A very slight learning slope, shall we
Yeah,
say.
yeah.
And of course, it's part of the Discovery family. So if you're familiar with the other instruments, it's all part of one big family. They operate in similar ways. They'll all be very familiar, and you should find yourself very
Oh, yeah.
easily able to move from one to the next.
Very. You should be very comfortable, working through, sample prep, method development, and data analysis. Yeah.
We did have a question early on from Kushbu, and I think this hopefully will be a quick and easy one to get us into there. What does the X3 stand for?
The X3 is, 3 times. Pretty simple and straightforward.
It says what it does on the tin is, I think, the phrase that people use about that sort of thing. I can see lots of good questions coming in. We did have a question earlier from Annie, and this is one of those ones that really puts you on the spot, because it's about using instruments in the real world with the complications that we all experience of trying to do things where there are people slamming drawers or there's a snow plow going past. So Annie said, right now, if they see a blip in one of 3 replicates, then they can be fairly certain that that's a vibration peak. And they can knock that out of their data because they know what that is from. But of course, if they have exactly the same peak, because you're running 3 experiments simultaneously, they experience the same vibration, that could be a lot harder to deal with. So does the X3 have improved vibration control, since it would be harder, or are there other things that you'd recommend to try and eliminate those sorts of real world problems?
Yeah, it's vibration control is certainly tricky. It's when you're it's a matter of the pan generally moving on the sensor. I'd like to think that in most cases people would be pretty cautious around your DSC when you're trying to make experiments. I know I share the frustration of someone slamming a drawer and creating a blip of some kind. Clearly, if all 3 of them have the same blip of the same magnitude, my guess is that the blip is associated with the sample. The DSC itself doesn't really have any vibration control, and so there is you have to be somewhat cautious where the DSC is placed. Some of our other instruments that have more critical need for vibration control, we have suggested a marble table of some kind to isolate the instrument from from outside impacts. I don't believe that I've seen instances where where a snowplow goes by and creates a blip, but I haven't seen it all. So but no, I there wouldn't be an improvement in vibration control or any more than what we have normally. But certainly I would say that this provides, I think running 3 samples at the same time gives you that extra level of benefit of checking it off that that either somebody slammed a drawer really hard, or there's actually something that moved all 3 of them at the same time, or that peak is actually associated with the sample. So that definitely gives you a little bit more added level of confidence in your interpretation.
Yes, thank you for your question, Annie. Good to remind us that the real world exists and not all situations are ideal. Shonak asked, is it possible to run 3 different types of experiments simultaneously on the X3?
Well, it's not. Obviously, there's one test that you're going to run, and so each sample is going to go through the same program. So if you want to start at minus 90 degrees and you want to ramp to 300, cool back down, and ramp back up to 300 again, all 3 samples are going to have to go through that same experiment. It doesn't mean that all 3 samples have to have that they have to be identical, and but certainly you're not going to be able to heat and cool the singular furnace at different rates or different temperatures for each individual sample. But you shouldn't be afraid to run 3 different materials as long as the range that you're trying to test in is okay and appropriate for those samples. I think that you're okay putting in some slight variations. But always want to be aware of where materials decompose. So you don't want to be breaking down materials at high temperatures. So that's really the only word of caution I guess I would have when running significantly different materials. But yeah, they're one program, one method. They all just see the same thing, but they don't have to be the same material.
So one sort of heating and cooling regime, but yeah, the materials can be as distinct as you like.
Yep.
That's good to know. Alex said, thank you for the nice presentation. So props to you, Jason, there from Alex. He says, he appreciate the high throughput, etc. But when should we use the DSC 2500 and then the X3?
So, there are some cooling options that are different. The 2500 allows you to utilize a finned air cooling system, which gives you a little bit higher temperature range. So if the upper limit on the X3 is, I think, 550 degrees. So if you did have experiments that you wanted to run between 550 and 725, the 2500 would be, your, I'll say, not your only option, but it's the option beyond the X3. There is also a direct heat capacity signal that you get with the 2500. The baseline reproducibility on the 2500 is slightly better than the X3. So direct heat capacity is making a single traditional ramp 10 or 20 degrees C per minute and being able to extract heat capacity as a signal rather than utilizing modulated. So there is, that added benefit that still exists on the 2500 that doesn't exist on the X3. And there is, I will say, ever so slight difference in the resolution that you get between the two systems. So if your experiments, if the materials that you're looking for are maybe have some polymorphic transformations, and you really need to have good resolution or good separation between peaks, that you might want to consider the 2500 over the X3. But for the most part, the X3 is really butting up against the 2500 in terms of overall performance. So it would be, it's a tough debate between the two, but there are certainly a couple of other features on the 2500 that if they're critical for you, that you would want to go that direction.
In my experience so far, everybody I've talked to from Waters or TA Instruments have been more than happy to engage with the community and solve these sorts of problems for you, so that this is not something that you would need to get a concrete answer for in a webinar one Thursday afternoon. You can speak to to people like Jason, who will be able to look at exactly what it is you're trying to do and make really good recommendations about the pros and cons of the different systems. So we've obviously got a link up on the screen. We've also put a link out in the chat in GoToWebinar. So if it's easier than typing down what you can see on screen, just click on that link and bookmark it for later. But the guys, everybody I've spoken to at Waters and TA, always really happy. They consider it really part of their mission to be embedded in the community. They're not just providing a tool for the community, they are part of it. So if you do have those sorts of questions, follow up with Jason, have a look at the website. You will be able to find other people to talk to who will help you work out exactly the right balance you need. You talked about auto calibration, so we've had a question from Seha who says, how easy is calibration of the equipment compared to the older generation?
Yeah, again, it's because you're only setting up one experiment, or one test to collect information on 3 samples, the calibration is virtually identical to what you would utilize in a Discovery, even in a Q series before that, if you're used to that generation. It's there are no extra steps except for the fact that you have 3 samples that you have to weigh out. So you're making indium measurements on all 3 samples. So you need to have an indium on each sample platform. If you're familiar with the Tzero sapphires, that you'll have more sapphires, but you'll have the same number of experiments from to accomplish your calibration. Then same number that you would have on the older generation. So again, as I talked about from a learning curve perspective or a learning slope perspective, it's a very gentle, gradual slope. Few more boxes to fill in because you have 3 samples, but certainly I would say very little extra effort in the X3 compared to our older generation.
Thank you for your question there. Pintu has asked a couple of really good questions, actually. To sort of slightly taking a step back, Pintu says, how is DSC different from differential thermal analysis?
So I'll say, differential thermal analysis in many ways doesn't have a heat flow component. So it's just a difference in temperature that you might see. So as you go through an experiment, an exotherm would have an increase in temperature versus a reference. An endotherm would have a decrease in temperature versus a reference. Once you start to get to the calorimetry part, the differential calorimeter, you're taking in, you're essentially taking that temperature difference and associating it with a heat flow, something that you can quantify in joules and joules per gram. So there is an energy component associated rather than just a simple temperature difference component. So a lot of high temperature equipment tends to be DTA, where the lower temperature regime is very commonly associated with DSC, the calorimetry part of it. I hope that answers your question.
Well, it actually leads us very neatly, and Pintu clearly knew what they were doing here. It leads us very neatly into Pintu's second question, which is, what's the normal scanning range and what's the maximum temperature?
So, I will say, traditional DSCs commonly range from about -180 on the low end to about 700, 750 degrees. So most DSCs that you would directly compare to the X3 or the other Discovery DSCs that we have are kind of in that -180 to 725, 750 temperature range. We have a simultaneous system that has DSC capabilities up to 1500 degrees Celsius, and so there is we use a piece of sapphire to calibrate it for calorimetry, but those are commonly I'll say categorized a little bit different, and so there are other instruments that can reach 1500, 1600 degrees, but they certainly they're not going to compare in terms of performance that you would see in a traditional DSC, because they're usually utilizing materials of construction to withstand temperatures of 1500, 1600 degrees Celsius. So there's no real exact answer, but that's kind of the general scenario that you see out in the world.
And once again, if your research calls for those sorts of temperatures, there will be somebody at Waters or TA Instruments who can help you, direct you to the right sort of kit that you'll need for that. So one final question: often these things are used, and we mentioned earlier, for QC, but can it also be used for a blue skies research instrument? Is this something that we would see in a research lab as well as being used in more industry for that QC purpose?
Oh yeah, I absolutely believe so. We have our R&D development team here at TA has really done, they made some really great innovations when they came out with the original Tzero cell, and another advancement in research and development of the current version of our Tzero DSC cell, and they really were able to take a lot of those high performance advantages from our standard system, incorporate those into this X3 cell. So, from a reliability, sensitivity, resolution, accuracy, all the things that really tend to matter to somebody doing blue sky research, those things are there and available on the X3 DSC. So it's throughput isn't always associated with, that blue sky idea where you might have just one formulation at a time, or, one composition at a time. Not that it can't make that measurement. I would, I don't have any concerns putting it into a, blue sky research. It just has that level of performance. And so, I would encourage anybody that, again, if you're wondering whether it's going to meet your need, we definitely have the folks here that can test it out and show you whether it can or not. So we want to be involved in that process as much as we can, make you feel comfortable with what you're going to spend your hard-earned bucks on.
Excellent. Well, we've run out of time now, but thank you so much, Jason, and thank you to everybody for asking your questions. I've got all the questions on the screen over here, which is why I kept looking over this way. I wasn't looking away from you. That is so yeah, that's all we have for this particular webinar, but we do webinars with Waters and TA Instruments quite often. They're a regular partner for us here at Chemistry World, a valued partner. We know they make excellent equipment, and we know that they, as I said earlier, they really embed themselves in the scientific community, in the chemistry community. So they're good people for us to work with. Do keep an eye out at chemistryworld.com/webinars for upcoming events. And while you're there, if you register for an account, you can sign up for our newsletters, and you can tick the box that says we can let you know about upcoming events as well, which means you'll never miss a Chemistry World webinar again, never miss an opportunity to speak to excellent people like Jason Saienga, who is the thermal analysis and thermal conductivity product management for TA Instruments. So, final reminder, we'll send you a link to the recorded version of this webinar in a couple of days' time. And for those of you who joined us live today, there'll also be a link to the certificate as our way of saying thank you for coming. So thank you to Waters, TA Instruments. Thank you very much to Jason, some of his colleagues that we've had in the background helping to marshal all of your questions. So many good questions. So thank you to everybody who attended live. I'm Ben Valsler, Chemistry World's digital editor, and we will see you in an upcoming Chemistry World webinar very soon. Thanks again.